Oh, I was just, whatever. Hey everybody, I'm Phil, and I'll tell you about Fil-C. So, what is Fil-C? So, Fil-C is a memory-safe language with absolutely no escape hatches. It's not like the fake memory safety of like Rust, where you can say unsafe anytime you want. There's no unsafe escape hatch. So the rules of Fil-C are always upheld. And it's safe to the point that you can't even link to unsafe libraries. So even the libc and libc++ are memory safe. And it's insanely compatible with C and C++. So lots of programs compile with Fil-C with no changes, and then a whole bunch of programs compile with like reasonable or minimal changes. CPython, for example, works with, I think, like a 50 kilobyte patch to CPython. I'm working on performance. It started out being like 200x slower. Right now it's 1.5x slower in like the good cases, 5x slower in the not so good cases. But I'm like on a trajectory where it's getting faster and faster all the time. So agenda for the talk, I'm gonna start with the demo because I just wanna lay the groundwork to show you that this is like a real thing. And then I'll talk about the goals, and then just a quick review of previous results, the key insights that make the thing work, and just a summary of the results, I guess. All right, demo. Let's do a demo. So, Fil-C, currently I'm developing it on my Linux box, Linux x86-64. There's nothing fundamental about it that's tied to Linux on x86-64. I just wanted to have something that I'm developing on. So, to start off the demo, to make it really fun, instead of using the shell that comes with Linux, I'm going to start a shell that I compiled with Fil-C. So this is the Z shell compiled with Fil-C. So the entire Z shell source code compiled with Fil-C running on top of musl compiled with Fil-C. So no memory unsafe code going on in there at all. Whoa, hey, look, I managed to make it crash with a memory safety error. Let's try that again. So, I mean, obviously, whoops, let's, you can see it's like it's, apparently on this computer when I press tab, it triggers something in there that doesn't work. So you can see when it crashes, you get a stack trace, and that's a really deep stack trace. And it's reading an out-of-bounds pointer somewhere in meta char len conv. Maybe that's an actual memory safety error in Z shell, or maybe it's just like, it's doing some C thing that I haven't handled yet. But whatever, we're gonna keep going with the demo. So in here, what I've got is I've got the URL for xzutils, and we're gonna git clone xzutils. This is gonna be spicy because, I mean, it's a live Git repo. They could have changed it. So I'm just gonna clone it. Git itself, I haven't compiled with Fil-C. I'm going to try to remember not to press tab. For some reason on my computer, on my other computer, when I press tab, Z shell is fine. So whatever, I'll debug it later. So we've cloned XZ. Or remember not to press tab. You can see that I'm running the omyzesh extension to Z shell, which further stresses it. So there's a whole bunch of code in Z shell that's interpreting this complex script that gives it all this styling, including the fact that it now knows that I'm in a Git directory and whatever. So here's how you port a piece of software to Fil-C. Well, first of all, since I've checked this out from, that time pressing tab worked, good for me. So I'm gonna run the autogen script, because you have to run the autogen script to get the configure script, as we all know. So now that I've got the configure script, to get this to compile with Fil-C, I'm just going to point it, oh good, tab is working now, I'm so thankful. Bin Clang, so this is my version of Clang. It's based on Clang 17, and then I'm just gonna do configure. So now you're seeing like multiple levels of demo of Fil-C. We're running a shell that's compiled in Fil-C, and then the configure script, what it's doing is it's compiling stuff with my compiler and then running it to test if it all works, to figure out what features are going on and whatever. So we've already compiled and run a bunch of Fil-C programs, but now let's get real and let's compile xzutils with Fil-C. So you can see that it's using the libtool thing to invoke my version of Clang. And let's see, it's probably already done compiling. Is it? It's almost done. Oh, come on, scroll down. There we go. Okay, cool. So we've compiled xzutils, and I'm going to use this xzutils that I compiled to compress libpslow, the runtime for Fil-C. So src xz libpslow.so. Let's see if this works. If you think it's slow, I'll show you how much slower it is than normal XZ in a minute. So it compressed it. Fantastic. No memory safety errors. That's great. And then we're going to decompress it. Oh, no, look at that. So I'm familiar with this bug. Basically, there's a part in xzutils on the decompression side where it uses inline assembly. When I say no escape hatches, I mean it. I don't allow inline assembly. Also, if you pass an out-of-line assembly file to my compiler will crash with an error. So now we're going to fix this bug, and we're going to fix it just to make it extra fun. We're going to fix it using a version of the MG editor. MG is an Emacs clone that I compiled with Fil-C. MG actually compiles and runs with no changes. Really cool. So I remember exactly where this thing is. liblzma, range decoder.h. Okay, so here you go. We're editing a text file in a memory safe text editor. It's written in C, but it's totally memory safe. And the issue is that in this header, it's got some macros that will either use x86-64 assembly or just C to do some stuff. So the way you detect if you're in Fil-C, this is my personal project, so I get to make stuff up. It's Pislinator was here. All right. So if not defined, did I spell that right? Pislinator was here. Cool, I spelled it right. So you can see Z Shell's like process management is working. This is important because Fil-C has memory safe signal handling and memory safe fork. So it's not just C, but like all of the universe of stuff that a C programmer on POSIX would expect works in Fil-C, and there's no escape from it. I won't have time in this talk to tell you how I made signal handling memory safe, but I did. So now we remake it so that we get a new version of it that doesn't have that particular bug. And there it is. So now we can try to decompress again. It's going to complain because when it last tried to, it already created the libpslow.so file, but didn't actually write anything to it. So now we decompress it. You can see that was pretty fast. So now let's look at how fast it is relative to like normal XZ. So we're going to time compressing libpslow. You can see compressing with XZ is actually, it takes some time. It's like a sophisticated compression algorithm. So that's how long it takes. So 2.96 seconds to compress and 0.17 seconds to decompress if you're just using the normal stock XZ compiled with like a normal C compiler. But the one compiled by me, let's see how long that takes. So we're gonna time. Oh, whoops! It's not .xz. Let's actually use the right file name. So to compress libpslow with XZ takes 5.51 seconds, and then to decompress takes 0.26 seconds. Now, I don't want to do the math in my head of what the overhead is, so what I'm going to do is I'm going to launch CPython compiled with Fil-C in order to use its REPL to do the math. So this is memory safe Python. What's really cool about this is Python's huge and has like its own garbage collector, does all kinds of crazy stuff. It even uses shared memory IPC for parallelism during its install process. So this is like a properly make installed Python that's compiled all of its bytecode using this, because they don't have real threads, so they have to use multiple processes and shared memory IPC. And shared memory in Fil-C works and is also memory safe. So yeah. All right, so there we go. We're in a REPL. You can see it popped into the REPL very quickly because Python in Fil-C is not like super slow or anything. It's like reasonable performance Python, and it's all totally memory safe. So on the compression side, it was 1.86 times slower, so less than 2x slower than normal C. And then on the decompression side, it was 0.17, so about 1.5x slower. So in like the good cases, 1.5x slowdown. In the bad cases, bigger slowdown. That's where I am today. Not guaranteed that I'll be there tomorrow because I keep making it faster. You can see the job control just works. It knows that there's a suspended job. I can FG, then it sees that it was killed, and I can kill the shell. So yeah, so that's the demo. That's Fil-C like actually working for realsies. So now let me get back to my keynote deck. All right, so let me talk about goals. Like, what am I trying to do here? These are the goals in descending order of importance. The first is, so I could have just said memory safety, but I can't do that anymore because people are using the term memory safety to mean completely ridiculous things that aren't memory safety. For example, a lot of languages are memory safe but have an unsafe escape hatch that you have to use to be productive. Rust, I'm looking at you. I even saw a thing where someone was claiming that Delphi is memory safe, even though Delphi has manual memory management that's totally not safe. So like people are throwing around memory safety almost like if it's not C, then it's memory safe. So here's what I mean by memory safety. I come from a background of implementing JavaScript VMs and Java VMs. In JavaScript or Java, it's like any sequence of characters fed to the implementation will result in a memory safe outcome. And if it doesn't, it's like a priority 1 bug that the implementers will fix. So what I call this GIMSO, garbage in, memory safety out. So the rules that the language is upholding are upheld even under adversarial input. So the goal here is that if you get the Fil-C version of Clang to compile your C code, then that C code cannot escape out of Fil-C's protections. And those protections are meant to be meaningful from a security standpoint. So WebAssembly you can think of as being memory safe, but in WebAssembly you can do basically data-only attacks which are just as dangerous as remote code execution. You can go out of bounds of an array and start overwriting somebody else's array. In Fil-C, we protect bounds, pointer integer type confusion, and use after free. Those are the big ones. And there's other stuff, but those are the really critical things. Bounds, pointer integer type confusion, and use after free. The next goal, which is almost as important, is compatibility with C and C++. I'm aiming for maximal compatibility to the point that, like you saw in my demo, I can run a configure script that I checked out from GitHub, just pointed at my compiler, and things basically work. That goal is secondary to GIMSO because if there's ever a contest between GIMSO and compatibility, I pick GIMSO. For example, I don't allow inline assembly even though I could. If I did, it would make me more compatible but less safe. Also, this is not a new compiler for C. This is Clang, and I'm aiming for a minimal change to Clang and LLVM. Just so like all of the good stuff in Clang that you expect to get as a Clang user is still mostly works. So like, for example, I can compile Daniel Lemayere's SIMD UTF library and run it just fine because since I am Clang, I have all the Clang SIMD intrinsics that Lemire loves to use, and they just work. And finally, reasonable performance. I deliberately put that one last. You know, if I was doing this to try to get a paper at PLDI, then I'd have to put that one up here. But I'm not. So I'm going for something. To me, I think it's an interesting intellectual outcome if I can make the C language, like if I can make an implementation of the C language that's compatible and completely memory safe, even if it is super slow. So performance is like, it's not a non-goal, but it's the least important of these goals. But I did specifically pick a non-goal very deliberately, and that's binary compatibility with YOLO C. That's what I call like normal C. So if you hear me say YOLO C, that's regular C. This is a non-goal that I picked primarily because the pointy-haired boss in me wanted to like have a scope reduction to make this like project realistic. But it's actually also kind of an asset that I have this as a non-goal, because if I had ABI compatibility with YOLO C, then it would incentivize me and other users to say, okay, I'm going to recompile this file with Fil-C link it to a whole bunch of files that are normal C because I don't want to be bothered with porting them. And then what you'll get as a result is a program that is not memory safe. I think that in order to get a memory safe process, like the thing that makes like Java or JavaScript or TypeScript memory safe is that substantially all of the stuff in there is memory safe, not that like 10% of it is or something like that. So not having ABI compatibility is kind of an asset. And guess what? If you want to link against somebody's C library in Fil-C, you can just recompile it in Fil-C because it's so compatible. All right, so previous results. Part of the reason why I was motivated to do this is that this is kind of like a scoured territory of solved problem. Like there's so many approaches that people have tried to make C memory safe, and so many of them were substantially successful. But if you add the GIMSO goal, then a lot of them fall off. Softbound and effective SAN both got really close, but they didn't handle corner cases of the language. Things like checked C and circle and F-bound safety are like opt-ins. In the case of checked C and F-bound safety, they only handle spatial safety, so type confusion use after free is not handled at all. ASAN MTE is probabilistic. WASM RLBox native client, they give you a sandbox, but they don't actually make the code running in that sandbox memory safe. So most of these don't actually give you the GIMSO goal. And then if you want maximal compatibility, then Safe C, JNK, they couldn't even handle C++. Cyclone's a completely new language. C-cured required that you write your mallocs in a very idiomatic way. And that's if you use their static analysis to convert to the real C-cured, which actually was a different language. So that kind of leaves Cherry. Is this showing me the, oh, this is like, I'm one slide behind on this or something. Oh, there we go. I hope I wasn't one slide behind the whole time. That leaves Cherry, but I actually think that Cherry isn't really compatible because it's whole new hardware. I wouldn't be able to run Cherry for you in a demo unless I ran it in QEMU or some IoT device that's hard to get. And if I did, it would be a lot slower than Fil-C is in practice because I would be running either in an emulator or on a really bad CPU. So Cherry succeeds at like source compatibility literally, but fails at the other kind of compatibility, which is can I run it on like the computer that I actually have. All right, so key insights. So nobody's achieved those two like top goals that I have, which is compatibility and GIMSO. So that's what makes Fil-C new, is that I actually try to go there. But I would point out that like this work wouldn't have happened if it wasn't for all of these past attempts. Fil-C takes massive inspiration from C-cured and from softbound and effective SAN. So, you know, it's cool that people did this research. So here are the key insights of Fil-C. First of all, I'm just going all in on garbage collection, and I'll tell you why. It's actually really great. It's my favorite part of this, is that it's garbage collected. The fact that it's garbage collected enables the capability model, which then gives me that maximum compatibility. The capability model is called monocaps. It's a novel capability model for C. If you read the literature on memory safe Cs, the way that one paper distinguishes itself from another is the capability model. This is a completely new capability model that I'll be telling you about. And then I'll tell you about the runtime, which is what I call the libc sandwich. And then finally, I'll tell you about how just a little bit about how I achieve GIMSO and LLVM. So garbage collection. It's like my own garbage collection algorithm. It's accurate, concurrent, non-moving. I could probably do a whole talk on the GC algorithm itself. If you're familiar with the Doliget-Leroy-Gonthier concurrent GC, it's sort of like that, except has a cheaper barrier. It's an algorithm I've used before. I have high confidence that it's decent. And it's definitely not the longest pole in the tent in terms of performance. That 1.5x slowdown you saw in XZ was not due to the garbage collector. It was due to everything else. So why have a garbage collector? The first reason is that it gives me a deterministic answer to what happens on use after free. A lot of these other approaches to memory safety in C kind of throw their hands up in the air for use after free. Like you can use after free in softbound. You can use after free in effective SAN. You cannot use after free in Fil-C. And then the other thing that it gives me is that it gives me these monotonic capabilities. So what the hell are monotonic capabilities? So if you're passing around a pointer in Fil-C, you're passing around a 128-bit thing, And 64 of those bits are totally under your control. The raw pointer is totally under your control. You can use pointer arithmetic to make it point anywhere in memory, including out of bounds of whatever object it's supposed to be pointing at. The other 64 bits are not under your control, but they are carried with the pointer as you pass it around. And those other 64 bits point at a GC allocated capability object that describes where the raw pointer could dereference what. So here's what it looks like. Gosh, okay, there we go. I was worried that I was one slide behind again. So the capability is currently kind of big. I'm working on making it smaller, don't worry. It's got a lower bound, an upper bound, some flags, and a 1-byte word type for every 16 bytes of payload. So the raw pointer can point anywhere in the payload or even out of bounds of the payload. The capability pointer always points at the base of the capability object. And in the common case, like if you call malloc, this whole thing is actually one GC allocation. The payload is just at the end of the capability. But that's not always the case. It's just the common case. So for example, if I call malloc 48, note that unlike something like effective SAN or secured, there's no need to annotate this malloc call with what the type is going to be. You call malloc 48, and what you get is an object that is 0 initialized in the payload, and the word types are all initialized to unset. That's where the monotonicity comes in. Each word type can monotonically transition from unset to either int or pointer, and then monotonically from there to free, but not ever in the other direction. So when I happen to store the first word with an integer access, that monotonically transitions that first word from unset to int. And then when I do something crazy, note that this is like so crazy that maybe the C spec doesn't even allow it. Who cares about the C spec? Like if you're writing a C compiler, you don't implement the C spec. You implement like the C that real people use. So real people do that. So if you're implementing a C compiler, you have to support it, and I support it. And the way that that works is P plus 4 is at offset 16, so that puts you in that second word. That second word started out as unset, so that store succeeds in transitioning that word type to putter. So that store just works. And then when I free the thing, then all the capabilities monotonically transition to free, and at that point, all accesses to that object will fail. Moreover, once the capability transitions to free, then on the next garbage collection cycle, when the garbage collector finds this pointer, it'll, rather than marking the capability in the payload, it'll just repoint the capability at the global free singleton. So freeing an object causes the next garbage collection cycle to really free it. This is important because if you take a malloc and free system and throw a garbage collector in it, you often will create memory leaks that weren't there before because people just kept around dangling pointers and happened to never dereference them. But in Fil-C, that is not the case. If you enable Fil-C, you're not creating new memory leaks because the freed objects do get freed. It's just that the actual reclamation of memory is deferred until the next garbage collection cycle. So monocaps give me this combination of maximal safety and maximal compatibility. There's no need to annotate or infer the type of malloc calls. You just call malloc however the hell you want. And then the types of that malloced memory are inferred dynamically, and the free itself is deterministic. After you free the object, every subsequent access to the object is guaranteed to fail, no matter what. So some additional monocap capability features that I won't be able to talk about because they're actually kind of deep. Function pointers, monocaps tell you about function pointers so that you can't get type confusion from indirect function calls. Monocaps handle mmap and munmap, including shared memory uses of mmap, so you can do shared memory IPC, memory safely with Fil-C, and it just works. They handle DSO handles, so you can do DL open and DL sim, so dynamic linking with Fil-C. That's memory safe, and it just works. Threads, jump buffers. Fil-C has long jump and set jump are memory safe. And the rules of long jump and set jump are dynamically enforced, so you can't set jump to somewhere you're not supposed to be set jumping to. And signal handling, so signal handlers work. So like you can register a signal handler and long jump out of it, whatever. Like so long as you're doing it the way that the manual tells you you're supposed to, it'll work in Fil-C. So how does the runtime work? I call it the libc sandwich runtime. In general, on any OS that you would port Fil-C to, what you would do, oh my gosh, I'm one slide behind again. Okay, there we go. What you would do is you would run the Fil-C runtime on top of whatever the libc is on your OS, just so that Fil-C's runtime can get syscalls. And then you compile that libc with Fil-C and run it on top of libpslow. So that but also make changes to the libc so that normally libcs make syscalls with like inline assembly or standalone assembly files, but the Fil-C version of the libc makes syscalls by calling into private API exposed by libpslow. And then libpslow filters every syscall for memory safety. So you can't use syscalls to escape memory safety. There is no escape. Fil-C will crash the shit out of your process if you try to escape. And then just compile all the rest of userland with Fil-C on top of that, and you get a memory safe application. Gosh. All right, so the current implementation, I call the musl sando. Musl is a freely available libc for Linux, and so I'm running YOLO musl below and user musl above. The YOLO musl is basically unmodified. The user musl is modified just to change how it does the syscalls. Here's an example of like how that ends up working out for a very simple system call. You can see like if you do the right system call in the user musl, it's just going to call an internal API called zsyswrite. That's all it can do. And then zsyswrite is implemented in the libpslow runtime, and it's first going to check pin and track the buffer, check that it's an integer buffer that it can be read from, and that there's size bytes of integers available in it. It pins it so that the garbage collector doesn't do anything funky, and then there's this Fil-C syscall wrapper around the actual syscall that does the thing that accurate GCs do, where it tells the GC, okay, I'm making a syscall now, so I'm at a safe point. And then YOLO musl does the syscall the way that musl usually does, which is with its macro that expands out into a bunch of inline assembly. So that's the basic pattern of how like syscalls look like in Fil-C. Okay. And syscalls are the only case of foreign function invocation between Fil-C and legacy C, and it's that foreign function interface is not exposed to anything other than libc. So there's a ton of complex features that just work. For example, I'm still one slide behind. So for example, C++ exceptions just work because libpslow provides a comprehensive unwinding API. mmap, shared memory, dynamic linking, signal handling, fork. You can fork. You can start multiple threads and then fork. You can cause the GC to run and then fork. All works. So yeah, lots of stuff just works. So how do I do this inside of LLVM? This insight that I'm going to tell you about is like one of the things that got me started on the project, and it's just a little bit of inside baseball about how LLVM work. So this is the LLVM pipeline in like very coarse grain box diagram. You got Clang. Clang does code gen, and then you get the whole sausage factory that is LLVM. Here's the insight. So in LLVM, there's the only pointer type is just pointer. You know that it's a pointer and you know nothing else. You don't know what it points to. In Clang, you have like a whole AST that describes C types, which don't really mean anything because in C you can cast anything to anything. But the way Clang code gen works is it's remarkably well behaved with respect to pointers. Namely, what I call the pointer versus integer intent is preserved. That is, if in your C program you had a variable or a field or something whose type was either pointer or reference or anything you would think of as a pointer as a C programmer, then that field, all loads and stores to that field or that local variable is going to be transformed into LLVMIR that says PTR for the type of that thing. So when you're looking at LLVMIR, you have now, LLVM can bitcast pointers to integers. So as soon as you actually run the LLVM optimizer, the intent is no longer going to be preserved. But at that precise moment when you came out of Clang code gen, the integer to pointer intent is preserved. So you have something that's almost like an emergent type-safe language where the only type is pointer versus everything else. And this is generally true for a lot of things. There's a couple of places where it's not, where it's not true. It's not true in the CG atomic portion of CodeGen. There it does bit casts between pointers and integers in weird ways. And some of the implementations of sophisticated C++ language features also do weird bit casts. But those are all easy to fix. There's no like profound reason why it does that. So here's how I implemented version 0 of the Fil-C compiler. I add the fil-pislinator pass, and that pass enforces GIMSO not on C, but on LLVMIR itself. So no matter what LLVMIR you give it, the output will be a program that enforces that pointer to integer intent of that IR. So every pointer load does checks that it's loading from a memory address that is allowed to be a pointer. Every pointer store does the, and then every integer load and store does the corresponding checks. All allocations are diverted to my runtime, et cetera, et cetera. So this is, you could give the pislinator pass any LLVMIR you like, and you'll either crash the pass, or you'll get a program that crashes with a Fil-C panic. You might violate the rules, right? Like if you do bit casts that are bad, or it'll run and it'll run memory safely. And so then version 1 was I just started adding more optimizations to run before the fil-pislinator pass. So I'm running most of the core LLVM meat grinder of optimizations. So it's the inlining fixed point that does SROA, which is like escape analysis for locals, GVN, which is load elimination, and other kinds of CSC, inst combine, a bunch of other stuff. And then to make it even better, I then added an abstract interpreter to the fil-pislinator pass so that instead of emitting checks blindly, I'm emitting a minimal set of checks for some definition of minimal. It's not like the best abstract interpreter you could possibly make, but it's a decent abstract interpreter. So results so far. I can compile bzip2, zlib, mg, both of the versions of PCRE, as if you're familiar with the Perl compatible regular expression library. There's like 2 of them. And ncurses, those compile with no changes and just work. And then there's a bunch of stuff that work with small changes, including CPython, SQLite, Lua, OpenSSH, so I can run the OpenSSH server and client, OpenSSL, links, so I've got a memory safe web browser, libc++ and libc++ ABI, anyway, a bunch of stuff. In the best case, it's like 1.5x slower than normal C right now, and in the bad cases, it's like 5x slower. But it's getting faster and faster. I'm working on another speed up right now. So the 5x number will keep shrinking. All right, that's my talk. Thank you.
Hey, Phil.
Hey.
Good to see you. Great work. I've long said that C and C++ are secretly safe languages. It's just the implementation. So I'm really glad to see this work. I guess I have some like high-level questions and low-level questions. I'll just be brief. High level, like how far do you want to take this? What's your goal? A medium level one is what do you think the major sources of slowdown are? And which ones are going to be tractable to reduce and which ones not so much. And then low level, I couldn't help but see that you have this word-based capability boundary. What happens if you do crazy things at a subword level, or is that just like a thing? Like if you were at a subword level, yeah.
Okay. So the first one, remind me. High-level goal. I want to troll a compiler team into making something better than this. So that would be the best outcome. Or to get somebody to actually use this in a serious enough setting that it just kind of takes on a life of its own. Either one of those. Mid-level, remind me. Performance. So the number one reason for the 5x is that the monotonic capabilities really are memory safe, are really thread safe. So when you do the first store to a word, it's a compare and swap to compare and swap that word type. And my next change is about just getting rid of that, changing the capability model a little bit so that I don't have to do that. And if you do subword, then like you still check the whatever 16-byte word you're in. So the part of what the abstract interpreter does is it like looks at all of the accesses to a range of memory and finds like the minimal set of instructions to check. That gets hairy, but that's how it works right now.
So would Cherry hardware alleviate some of that performance?
Cherry
issue?
hardware would make it so I can't run CPython.
And why is that?
They can't run CPython because there are nasty things in the CPython bytecode where the way CPython normally does it is it stores 64-bit pointers. They have to be 64-bit, like it's very hard-coded, on 2-byte alignment within the bytecode stream. So that completely breaks Cherry. And because I have a garbage collector, there's like having a GC means that you can do these localized hacks where like, oh, I have a lookup table here. I just allocate it. Who cares when I free it? So I was able to very straightforwardly like make that code just work so that it's storing a 64-bit index that then happens to get looked up in a table. But the Cherry people never were able to get that to work. So on Cherry, the best you could do is MicroPython. And I suspect there are going to be other cases of this. Basically, having a GC means if you find yourself in a region of someone's code where like the capability model is too strict, it's too much of a straitjacket, you have this like off-ramp where you can be like, well, but I have a GC, so I can just like malloc myself something and not worry about it. So I wouldn't want to run on Cherry because like it would make me less able to run stuff. Also, silicon economics are all about volume. So like Cherry wouldn't be a speed up for me right now. I guarantee you any hardware you can get that runs Cherry is going to run XZ slower than I just ran it. So like the correct way to get better performance is to keep running this on stock hardware, and then if it gets big enough, then the CPU designers are going to use traces of Fil-C's checks in their optimizations, and then it's going to get faster.
You didn't say anything about what doesn't work. So, for example, can you XOR 2 pointers together and expect things to come out right?
First of all, in C, if you tried to XOR 2 pointers, that is one case where the compiler will actually give you a compiler. You can cast them to
integer and XOR.
And yes, you can do that.
And it works.
The main thing that doesn't work is pointer-integer unions where you change your mind about whether you're using pointer or integer. And I'm actually, the change that I'm working on right now that's also going to be a speed up also puts me in a mode where I can allow unions to flip-flop. So I'm like, when I become aware of something that doesn't work, I fix it. But the biggest practical thing that sucks is if not having inline assembly means that like any sufficiently large C program doesn't compile immediately out of the box because you have to, at a minimum, just tell it not to use the inline assembly.
Hi, we're the CPython devs that introduced those inline bytecode caches, so sorry about that.
Oh, no problem.
But you mentioned that it needed some changes. Are those compatibility things like support for fat pointers mostly, or is it working around bugs in the implementation, or are they true memory unsafeties that need to be upstreamed?
There was one memory safety bug that I found, and I filed a bug, and y'all fixed it the same day. It was super awesome.
Awesome, thank you.
The other stuff is like, for example, in the GC implementation, the header in the way CPython is written uses uintptrt. I just had to change that to void star to make that work. So like you could imagine upstreaming that to CPython and it wouldn't make any difference whether it's void pointer or uintptrt for people compiling with normal C, but you can't use uintptrt because as soon as you cast a pointer through uintptrt, once you cast it back to a pointer, you get a pointer with a null capability and you can't access it. So if you want to actually play games where you have a pointer, even pointer like that uintptrt has like high bits, low bits, whatever. You can do that with a void star. It just has to stay a void star if you ever want to go and dereference it. So that's like the biggest change is, that's why it's like a 50 kilobyte patch, because once you change the types of those fields from uintptrt to void star, there's like multiple files where you have to kind of, adapt to that.
Hey, thanks. Two small questions, I guess. The first one is, so does it have like capability with LLDB for like debugging capabilities so far? Or okay, cool.
No.
That kind of makes the other one moot. Then never mind. Thank you.
I want to add that. It's just that, like, I completely corrupt the dwarf in my transformation right now. I'm not preserving it at all.
Hey, some nuts and bolts questions about the GC. Do I understand correctly, since there's no stop the world, it's a fully concurrent, you don't have the problem of figuring out where to put save points because you just don't need them in like a multi-threaded program?
No, it's like it uses the soft handshakes that you would find in a DLG collector. So there are pull checks, as I call them, sprinkled by the compiler. Also on the slide where I had right there, Fil-C syscall has to do, actually calls Fil-C exit before the syscall and Fil-C enter after it to tell the GC, hey, you don't have to wait for a pull check from this thread right now. So it does all the things that you would expect like a Java VM's GC to do in order to interact with the mutator. But there's no global stop the world where you like stop all the threads at once and then do some stuff. It's the GC asks, hey, all threads, please check in with me. And then when they all do, then the GC makes progress.
Thanks. Second unrelated question. So you said you'd rely on this invariant that happens to hold in Clang CodeGen. Is that an emergent invariant? Like, do the Clang team care about that in the long term, or what?
Thank goodness for GPUs, man. It's an invariant that they, I think, had to enforce because the pointer integer distinction is particularly meaningful when you're compiling things like OpenCL. So I think that's why they're careful about it.
Thanks.
But if I was writing a C compiler today and I wasn't in the business of memory safety, then my intermediate IR wouldn't even have a pointer type. I would just have integer types, and my load instruction would take an integer, which is, by the way, what I did in the B3 backend in JavaScript core. It just has integers. So if I was in a world where I had to convert my own C compiler to Fil-C, then I'd be completely screwed because I wouldn't even have a pointer type. So there's the danger that like in there's some future version of LLVM that just gets rid of the pointer type. And then I'd be sad and the GPU people would be sad.
So I'm sure you're aware that the Rust people are super excited about the documents coming out of the federal government regarding safety.
Yeah.
And they're convinced that they're going to be the torchbearers, right? And will strip C and C++. So I guess I have two questions about this. I mean, once you make CPython actually memory safe, then Python is safe modulo all those packages that aren't safe. But in principle, you could recompile them.
You
right?
have to in Fil-C.
Yeah, right. Which is a challenge, I expect, but not such a challenge for things like NumPy and stuff. Like,
Right.
The only question is if they call out to BLAS, that's going to be a deal breaker. So performance is going to be a killer in that space. I feel like there's things like OpenSSH are the sweet spot for this kind of work, like very clearly security sensitive, internet facing things. So I mean, I would propose that rather than just hoping that some compiler team picks this stuff up and runs with it and makes things even faster, that you make it available as a tool, if you can, that people can use to build this software when they just want hardened OpenSSH.
It's available today. Like you can go on GitHub and check it out and build it. If you're on Linux x86 64, it just works. So I actually think that part of the reason why I'm doing this is I want to obviate the need for Rust. And so like I'm not there yet performance-wise, but I will get there. And if you have suggestions for how to con people into using it, I'm all ears. I mean, this is a brand new project, right? I started in November of last year, so I have had only a small number of opportunities to even. This is the first time I'm talking about it publicly, for example, other than YouTube, and trolling people on Twitter.
I think since it's been a bit over time, we can go ahead and go to lunch and then take the rest of the questions offline. So let's thank our speaker again.
Thanks, y'all.